Thank you, Dick, for an overly generous introduction. I realize the hour is late, you're tired, and I'm tired, so if I have a few amusing stories sprinkled around here and there amid the science, you'll understand why and probably appreciate it very much. Start with, you can't possibly expect to discover an enzyme that you don't know exists, that acts on an unstable substrate, that nobody believes exists or has anything to do with biology. When I started working, I had this terrible habit of being diverted by every interesting observation, so I'd go from thing to thing, and I actually began to worry about that. And so I went to a wise old chemistry professor named Vosburgh, and I hope I get this right, and I asked Vosburgh, was that a good thing to do, or was it better to stick to one problem and stay with it? And he said to me, well, you never know. Suppose you're in the forest hunting rabbits, and you're following a trail of rabbit track through the snow, and suddenly you see another rabbit track crossing the one you're following. What should you do? And I said, well, I was waiting for a kernel of wisdom. And he said, well, you never know. Maybe, maybe the new track is fresher than the old track. Maybe the rabbit that made the second track is fatter than the rabbit you made. So I thanked him, and I left with the feeling that he was giving me a blessing to continue as I was doing. It was all right. So let me begin with what is superoxide. Simply stated, it's an oxygen molecule with one extra electron on it. Here it is. It's a conjugate base of a weak acid. The hydroperoxyl radical, the pKa is 4.8. So at neutral pH, less than 1% of it is HO2, and it's almost all O2 minus. It was proposed first by Linus Pauling when he was studying oxides of potassium. And then it was observed actually by radiation chemists who noticed a transient conductivity in radiated water if oxygen was dissolved in the water. And using that method of radiolysis, they were able to produce superoxide at will, and they used the method to allow them to calculate the rate constants for dismutation reactions, the absorption spectrum, and so on. So it was known to radiation chemists at the time. But, you know, I followed one thing after another until I started to study xanthine oxidase. And xanthine oxidase is a fascinating enzyme, complicated, different kinds of prosthetic groups, flavin, iron sulfur clusters, molybdenum, molybdotterin, as Rajagopalan discovered. And also, it's not very specific with respect to its substrates or its electron acceptors. It'll catalyze the oxidation of a host of purines, purine to hyperxanthine, hyperxanthine to xanthine, xanthine to urate. It'll oxidize a whole bunch of different aldehydes to the different carboxylic acids. But it's not even very specific with respect to what it will transfer electrons to, because it'll reduce oxygen. In the absence of oxygen, it'll reduce various dyes like methylene blue, dichlorophenol, indophenol, and so on. It'll even reduce nitrate to nitrite. And then there was an observation made by Horaker and Heppel that it would reduce cytochrome C, but there was a really peculiar aspect to this. It would reduce the cytochrome C not in the absence of oxygen, but only in the presence of oxygen. And they explained that by saying, well, the enzyme makes H2O2, hydrogen peroxide, and hydrogen peroxide is the reductant of cytochrome C. And they left it at that. So they didn't have my habit of skipping from thing to thing, or they had bigger fish to fry. I don't know what the situation was, but it really caught my attention. And of course, it didn't take long to show that H2O2 would not reduce cytochrome C at all. So if it wasn't divalently reduced oxygen, maybe it was univalently reduced oxygen, superoxide. And there was a meeting in Atlantic City of the American Society of Biological Chemists, and I had a 10-minute talk, and I presented the data and suggested that xanthine oxidase was making superoxide. Superoxide was reducing cytochrome C. Well, there was a very distinguished physical chemist, British, named Philip George, and he stood up at the end of the talk, first question, and said, "That's impossible." And in case it's not clear, Philip George is up there, and that's me. Naturally, I was embarrassed, and I didn't quite know what to say, but I said, well, it fits all my data, and on top of that, why do you say that? He said, why do you say it's impossible? He said, the redox potential of superoxide is minus 670 millivolts, and that's more negative than anything that's known in the cell. So I said, well, you know, maybe that's so, but if the superoxide remains bound to the enzyme, its redox potential might be different than superoxide in free solution, and I slunk away. But decided to simply ignore what he'd said and keep what I was doing. Now, I mentioned the dismutation reactions, and I did mention that superoxide is intrinsically unstable, and these are the reactions. Now, a dismutation is any reaction in which two substrates that are identical are converted to two products that are different. So you can, since I mentioned already superoxide was a conjugate base of a weak acid, you have to consider three dismutation reactions: H2O2 with H2O2, H2O2 with O2 minus, and O2 minus with O2 minus. And I've got the rate constants up there, and maybe I don't, I should tell you. Oh, this is the, I must have pressed it twice. I'm getting a tremor in my old age. There are the rate constants. So the HO2-HO2 reaction is fast, 10 to the 5th per molar per second. The HO2-O2 minus reaction is faster, 10 to the 8th per molar per second. But the O2 minus O2 minus reaction effectively does not occur, and that would be because of electrostatic repulsion between the two O2 minuses, not allowing them to get close enough to transfer an electron between them. Now, there is also enzyme catalyzed reactions, and the way to avoid the problem with the electrostatic repulsion between two superoxide is obviously to have a metal take the electron from one superoxide and then transfer it to the next, thus avoiding the necessity for close approach of the two anionic radicals. And here is the mechanism of the way the enzyme works. And I specifically wrote metal rather than copper or something, because as I'll say in a few minutes, there's a whole family of superoxide dismutases. And so the enzyme is, the metal is reduced, let's say it's a copper zinc enzyme, copper is the active metal. It's reduced by the first superoxide to cuprous, copper 1, and then reacts with the second superoxide, giving it the electron, and you've got your H2O2 and copper 2 back again to go again. Actually, it's not H2O2 that's made on the enzyme, it's HO2 minus ionized form of H2O2, dissociates, picks up a proton from the water, and you got your products. All right. Now we'll talk about the purification. So we knew that superoxide was reducing the metal. There was an enzyme, evidently some activity that was very abundant in every conceivable extract of anything you wanted to look at, bacteria, mammalian tissues, and that activity inhibited the reduction of cytochrome C, and remember that was oxygen dependent, without inhibiting the activity of the xanthine oxidase. That's key. And the way it could be doing that was by scavenging the superoxide, catalyzing its dismutation. So we knew we had an assay, and we set out, in this case, we meaning Joe McCord and me. We went to a slaughterhouse, we collected a gallon of bovine blood, we brought it back to the lab, and I said to Joe, you know, let's get rid of the plasma proteins first. So the cells were spun down and washed in saline. Then he said, what now? I said, well, you know, there's a guy named Tsuchihashi who was purifying catalase from red blood cells, or lysate of red blood cells, and he used chloroform plus ethanol to precipitate the hemoglobin, which is most of the protein in there. So if you can get that to happen without the enzyme getting killed, we're almost home. So he added chloroform ethanol, heavy precipitate formed, he spun it down, all the activity was in the supernatant. Yay! So he said, what now? I said, well, add ammonium sulfate, that was a common thing then, precipitate the enzyme. So he adds ammonium sulfate, and comes to me and he says, I blew it. And I said, what do you mean, you blew it? He said, look at this. It separated into two phases. There was a lighter organic phase, supernatant over a heavy salt water phase. And he was all set to dump it down the sink and start over again. I said, wait a minute, let's assay both phases. And all the activity was in the organic phase. Wonderful. So what next? And we used to use acetone fractionation a lot in the old days. I said add a number of volumes of ice cold acetone and precipitate the protein. And down came a blue-green precipitate. It was almost pure at that point, 100% recovery, run it through a ion exchange column, and it was pure, and so we were home free. Okay, now I mentioned that there's a whole family of superoxide dismutases. At this point, we were the only ones working in the field. We had the whole playground to ourselves, and so we looked in many different places and started to isolate enzymes with the same activity. They all had essentially the same activity, but they proved to have different metal ions. So the copper zinc family is found in the cytosol of eukaryotic cells. It's found in the periplasm, the space between the two membranes, of gram-negative bacteria. It's found in the intermembrane space of mitochondria. And of course, there was at the time a discussion about the endosymbiotic origin of these organelles, and the copper zinc SOD from the periplasm or the intermembrane space, and you know, it was just bang on. I mean, you couldn't miss it. This really had to be the result of an endosymbiosis from a prokaryote into a proto-eukaryote. It was just too beautiful. When we looked in E. coli, in this particular case, there are two SODs in E. coli. One of them is constitutive, made all the time, even when the cells are growing anaerobically, and that's an iron-containing SOD. It was isolated from Fred Yost in my lab. And there was an manganese SOD that was almost identical to the manganese SOD found in the matrix of mitochondria. And the manganese SOD was not constitutive, it was inducible by oxygen, or if you put in compounds that increase the superoxide production by redox cycling, compounds like viologens, paraquat, for example. And you can get the cell to make enormous amounts of manganese SOD by inducing with paraquat. We did that. That was done by Hasni Hassan in my lab. And then there's what are called cambialistic. I can't get used to that word. It refers to SODs that are found in certain facultative anaerobes that can have, it's the same protein, same gene product. It can have either manganese or iron and be active with either one. Whereas the iron or manganese enzymes from other sources are specific for the metal, and although you can replace the metal, let's say a manganese SOD, replace it with iron, it's not active, and vice versa. The cambialistic ones are active with either one. I think it was Mick Gregory who first noticed that. And surprisingly, no, not surprisingly really, when they produced the enzyme under anaerobic conditions, under which condition iron is iron 2 and soluble, they made the iron SOD. Under aerobic conditions, where iron would become iron 3 and insoluble, they put manganese in instead. Well, so why should there be so many SODs in every place? I think the way to look at this, of course, is that the superoxide is damaging to cells in ways that we'll discuss in a minute, which people at that time, first they hated the idea of superoxide at all, and then they had the fallback position, well, maybe it's made, but it's benign, it's no problem to the cells. These things you're calling SODs are really metal storage proteins. Rod, you remember Fee. He made a career out of doing that, saying that, to my extreme annoyance. Anyway, the way I look at it is that oxygen presently present in the atmosphere as a result of photosynthesis. There must have been considerable evolution in an anaerobic world before photosynthesis arose. And then when it started to accumulate in the biosphere, there had to be superoxide dismutases evolved to deal with the superoxide that would inevitably be made. And different organisms in different environments produced SODs with different metals, and they're still around. And of course, the second point is the superoxide doesn't cross membranes too easily. So wherever it's made, it has to be taken care of into intermembrane space. There has to be an enzyme there in the matrix, an enzyme there, and so on. Now, what's the advantage of SOD? I mean, the rate constants for the SOD catalyzed reaction is 2.3 times 10 to the 9th per molar per second. That's very fast. But the spontaneous dismutations are very fast too. And let's say at neutral pH, the spontaneous dismutation might go at the rate of 10 to the 5th per molar per second. The enzyme is 4 orders of magnitude faster, but that's not such a big deal. But you consider that the steady state concentration of superoxide in a typical cell, either bacterial or mammalian, is about nanomolar. The typical concentration of SODs in these cells is 10 to the minus 5th molar. Therefore, a superoxide has 4 orders of magnitude greater likelihood of colliding with the enzyme than it does in colliding with another superoxide that it can react with. So on top of the 4 orders of magnitude greater rate constant and the 4 orders of magnitude increased likelihood, you've got 8 orders of magnitude advantage provided by the SODs. And we've estimated, and this was Stefan Liachev, estimated that the SOD present in most cells is sufficient to intercept 95% of the superoxide that's made, and that's in competition with all the other targets for superoxide that exist in the cell. So O2 minus can damage things. What can it do? I wish Fee was still around so I could show him this. But at that time, it wasn't known that nitric oxide was made in cells and was very much a signaling molecule. O2 minus is a free radical. Nitric oxide is a free radical. Radical reactions are very rapid. So the superoxide nitric oxide reaction goes at 10 to the 10th per molar per second. That's diffusion limited. That means every collision results in reaction. And the product is peroxynitrite that you see. And peroxynitrite tends to homolyze into NO2 and hydroxyl radical, both extremely reactive species and would cause the nitration, for example, of aromatic amino acids such as tryptophan and tyrosine to the corresponding nitroaromatic acids. It'll nitrate unsaturated fatty acids to give nitrofatty acids, and they have their own secondary effects that are not very good. And then there are the iron-sulfur containing dehydratases, such as aconitase, or the bacterial fumarases, A and B. These enzymes depend upon 4 iron, 4 sulfur clusters at their active sites, and one of the irons in the cluster, that's a cubane cluster, is not linked to a cysteine. It's free, exposed to solution, and it reacts with superoxide about 10 to the 6th molar per second. And it has the effect of making the cluster unstable. It falls apart. It releases an iron. And there are 2 bad things about this. One is that the enzyme is inactivated. So if you inactivate the fumarases or the aconitase, you can't have a citric acid cycle going on. The second thing is, excuse me, you've released iron. And iron, of course, will react with H2O2 in what's called a Fenton reaction, in which case you get hydroxyl radical from the H2O2. And hydroxyl radical I've got down as the universal oxidant. There's a huge compendium put together by the National Bureau of Standards decades ago, rate constants for the reaction of hydroxyl radical with compounds. And if you look at it, it reacts with just about everything in the world, even straight hydrocarbons with no functionality at almost diffusion limited rates. So if it's made, it's going to do damage within a few collisions. And of course, if there's iron set free in the cell, it won't be in free solution. It'll bind to polyanionic things like nucleic acids, like membranes with the phospholipids. And so the hydroxyl radical would be produced there and would preferentially attack those compounds. Now, if you carry away one thing with you from this, I want you to keep in mind that superoxide is easy to make. In fact, univalent reduction of oxygen is the facile route. It's the preferred route. And the reason is the spin restriction, which I've got up here, and I'll just go through it very, very quickly. Okay, most stable molecules are diamagnetic, meaning all of their electrons are in spin-opposed pairs. Oxygen is paramagnetic, and the magnitude of that paramagnetism indicates that it's got 2 parallel electronic spins that cannot be in the same orbital. They have to be in different orbitals, which they are. So now imagine you're trying to oxidize that diamagnetic organic molecule with molecular oxygen, and you'd like to pair up the electrons, and you can see by inspection that one of those electrons could go into a spin-opposed position. The other would be in a parallel position in the same orbital, which is not possible. It's something called the Pauli exclusion principle. This is called a spin restriction. So oxygen is much less reactive than it might otherwise be, as evidenced by the fact that there's singlet oxygen. We won't get into that. Forget it, I'm sorry. Anyway, the way around it is to add the electrons one at a time, because electronic spins can be inverted by interaction with nuclear spins, but that's a slow process. How slow? Well, it's like, nanoseconds, but it's much slower than the lifetime of a collisional complex. So it's not going to happen while 2 molecules are in collisional contact, but there's all that time between collisions for it to happen. So you transfer 1 electron to the oxygen, it goes into a spin-opposed pair, the oxygen bounces around for a while before it makes the next collision, and during that time, the electronic spin on the oxygen is inverted, and you can transfer the other electron. So remember, superoxide is the easy product to make. All right, we'll call this inconvenient chemistry after Al Gore, all right? And what's nature's answer to inconvenient chemistry? Well, there's several. One of them is devise enzymes that somehow manage the divalent and even the tetravalent reduction of oxygen without releasing any intermediates. For example, cytochrome oxidase is responsible for most of the oxygen that is being consumed in our cells, in our mitochondria. And it manages to reduce oxygen to 2 molecules of water without releasing any intermediates. And then there are all those oxidases, glucose oxidase, the amino acid oxidase, etc., that make H2O2 without releasing superoxide. So that's the first answer. Make as little as you can. The second answer is the superoxide dismutases. And we're still not done because I said before they only provide about 95% protection. And so you need a whole host of other enzymes to repair the damage that is inevitably being done in all of us right now. And so, for example, I'll talk about E. coli first. There's a regulon, a group of genes that are not adjacent to each other in the genome of, should have had water up here, in the genome of the organism, but it's okay, I can get by. Oh, hey, thank you, sir. All right. Anyway, there's a host of enzymes that are regulated in response to exposure to superoxide. And I just give you an example. It's called the SOXRS regulon. One of the members of the regulon, of course, in E. coli is the manganese SOD, but then there are others. For example, I mentioned that the bacterial fumaraces, being iron sulfur cluster containing dehydratases, are inactivated by superoxide. Those are fumaraces A and B. One member of the SOXRS regulon is fumarase C, which manages the same reaction, hydration of fumarate to malate, but it doesn't work with an iron sulfur cluster, and it's not inactivated by superoxide. Aconitase is inactivated, so there's aconitase A and B, and one of them is part of the SOXRS regulon. There's a G6-beta-glucose-6-phosphate dehydrogenase. That's an important source of reducing power to damage, repair oxidative damage, and so on. So let's see, where am I? Oh, yeah. I got to tell you this story. I wanted to have the rate constant for the enzyme catalyzed dismutation, and I had no way to measure it, but I knew it could be done by pulse radiolysis. So I started to read the literature of pulse radiolysis and saw the name Joseph Rabbani, a physical chemist and working at the Hebrew University in Jerusalem. And he had the equipment and the know-how. I surely could do it. So I called him and asked him, and I expected him probably to say, don't bother me, I've got my own fish to fry, and so on. Instead, he was fascinated. He said, I've been waiting to have a biological application for this pulse radiolysis. And I said, okay, I'll send you the enzyme, and then you can make the measurement. And he said, listen, these people have been sending letter bombs to Israel. And if this package you're going to send me looks like anything other than junk, it's never going to get to me, because they'll hold it up in the post office and blow it up. So I thought about that for a day or two, and then got a 10-foot length of intrametic polyethylene tubing, the very thin polyethylene tubing, injected the concentrated solution of copper zinc SOD into it until I could see by the blue color that it was full, sealed the ends with 5-minute epoxy, formed it into a flat coil, put the flat coil in the middle of a reprint, used some Scotch tape to put it down, put the reprint in an envelope addressed to Sefi Rabbani, and as a final point, I didn't seal the envelope. So it clearly looked like junk. And he called me a few days later and he said, I got it. Now, here's my acknowledgments. How much time do I have left? Any time at all? If I do, how much? Oh, I'd love to tell one more story. I know you're tired. Neutrophils, macrophages, these phagocytic leukocytes can be activated. And when they do, they exhibit the respiratory burst. Their oxygen consumption increases 15 to 20-fold. It's really dramatic. And it's important in their killing of microorganisms that they're going to engulf, because there's a series of genetic diseases called chronic granulomatous disease where there are defects in the activation mechanism, and what's being activated is a membrane-associated NADPH oxidase that quantitatively reduces oxygen to superoxide. And the sense of it being in the membrane is the fact that when this organism is going to phagocytize, engulf a microorganism, what is the outside becomes the lining of the phagosome, so the superoxide is being directed, at the organism. Anyway, a student in Rajagopalan's lab named Skip Kessler had this bright idea that the respiratory burst was for making superoxide, and he presented it at a prelim exam. And I knew that. And then I went to a meeting in Atlantic City, and I ran into Bernard Babior, and Babior came up to me and said, listen, Irwin, I'd like you to give me some of that SOD. And I said, why? And he said, well, I got this idea that the burst is about superoxide production, and I'll use the SOD to prove it. And I said, Bernie, I'm sorry, I can't give it to you. And he was really taken aback. How could a friend do this to him? And he said, why? And I said, well, there's a kid in Raj's lab who made the same proposal, and I can't help you in competition with him. Well, it happened that Skip Kessler was not one of these following leads. He never did anything with it. But Bernie said, he was very understanding. He said, okay, I understand your problem, but you guys described a very easy procedure. I'll make my own, and we'll see. And he did a lot with the respiratory burst and with the enzyme. NADPH oxidases have been found in other places. Now there are 5 of them. The usual abbreviation is NOx. There are NOxes. All of them are making superoxide. So this is another take-home lesson. It's a really ill wind that blows no good. The cell has found a way to make superoxide and do something with it. In this case, help it kill bacteria or other microorganisms. And I think I probably stressed you beyond the point of your patience, so I thank you very much, and I'll take questions. It would reduce cytochrome C, but there was a really peculiar aspect to this. It would reduce the cytochrome C not in the absence of oxygen, but only in the presence of oxygen. And they explain that by saying, well, the enzyme makes H2O2, hydrogen peroxide, and hydrogen peroxide is the reductant of cytochrome C. And they left it at that. So they didn't have my habit of skipping from thing to thing, or they had bigger fish to fry. I don't know what the situation was, but it really caught my attention. And of course, it didn't take long to show that H2O2 would not reduce cytochrome C at all. So if it wasn't divalently reduced oxygen. Maybe it was univalently reduced oxygen, superoxide. And there was a meeting in Atlantic City of the American Society of Biological Chemists, and I had a 10-minute talk, and I presented the data and suggested that xanthine oxidase was making super. Thank you, Dick, for an overly generous introduction. I realize the hour is late, and you're tired, and I'm tired, so if I have a few amusing stories sprinkled around here and there amid the science, you'll understand why and probably appreciate it very much. Start with, you can't possibly expect to discover an enzyme that you don't know exists, that acts on an unstable substrate, that nobody believes exists or has anything to do with biology. When I started working, I had this terrible habit of being diverted by every interesting observation, so I'd go from thing to thing, and actually began to worry about that. And so I went to a wise old chemistry professor named Vosburgh, and I hope I get this right, and I asked Vosburgh, was that a good thing to do, or was it better to stick to one problem and stay with it? And he said to me, well, you never know. Suppose you're in the forest hunting rabbits, and you're following a trail of rabbit track through the snow, and suddenly you see another rabbit track crossing the one you're following. What should you do? And I said, well, I was waiting for a kernel of wisdom, and he said, well, you never know. Maybe, maybe the new track is fresher than the old track. Maybe the rabbit that made the second track is fatter than the rabbit you made. So I thanked him, and I left with the feeling that he was giving me a blessing to continue as I was doing. It was all right. So let me begin with what is superoxide. Simply stated, it's an oxygen molecule with one extra electron on it. Here it is. It's a conjugate base of a weak acid, the hydroperoxyl radical. The pKa is 4.8. So at neutral pH, less than 1% of it is HO2, and it's almost all O2 minus. It was proposed first by Linus Pauling when he was studying oxides of potassium. And then it was observed actually by radiation chemists who noticed a transient conductivity in radiated water if oxygen was dissolved in the water. And using that method of radiolysis, they were able to produce superoxide at will, and they used the method to allow them to calculate the rate constants for dismutation reactions, the absorption spectrum, and so on. So it was known to radiation chemists at the time. But you know, I followed one thing after another, and so I started to study xanthine oxidase. And xanthine oxidase is a fascinating enzyme, complicated, different kinds of prosthetic groups, flavin, iron sulfur clusters, molybdenum, molybdotterin, as Rajagopalan discovered. And also, it's not very specific with respect to its substrates or its electron acceptors. It'll catalyze the oxidation of a host of purines, purine to hypoxanthine, hypoxanthine to xanthine, xanthine to urate. It'll oxidize a whole bunch of different aldehydes to the different carboxylic acids. But it's not even very specific with respect to what it will transfer electrons to, because it'll reduce oxygen. In the absence of oxygen, it'll reduce various dyes like methylene blue, dichlorophenol, indophenol, and so on. It'll even reduce nitrate to nitrite. And then there was an observation made by Horaker and Heppel that